record. Okay, so if you guys don't have any questions, I can start with chapter 1. Any questions? And please stop me, jump in there, ask questions, don't be shy. That's not gonna work for you. All right, so again, I'm hoping that you have read some stuff. I'm just gonna go over some stuff. If you need me to explain more, you're gonna ask me. And so we're gonna go from there. So first part of this chapter is talking about the computer system. I'm hoping that most of you have looked at that already. Talking about the problem solving. We're gonna touch how to do the C++ programming and testing and debugging. That most likely I'm gonna leave that to you to read it in more detail. Okay, so when we're talking about the computers, we're talking about the hardware and we're talking about the software. Hardware is a physical computer. Software is the programs that are on the computers. And technically, softwares do not exist in the world. Those are virtual stuff. So the physical things and virtual things. A physical one that it does exist in the world. Virtual one, just like my name, does not actually, my name doesn't exist in the world. I live in the world, but not my name. So we talk more about that later. So we have editors, translators, system managers, PC, workstation, mainframe. I'm not going to go through those details. Network, input device, output, CPU, main memory, and secondary memory. You should spend a lot of time in these things. They are going to show up in your test on Friday. So I'm going to go over this one. It has a picture like this. So we can so what do you think a CPU is?
I think the CPU is like the brain, like it's the part of the computer that does whatever you tell it to do. That's what I think it is.
Okay, anybody else?
So take care harder part of the calculation compared to the GPC, the other easy one.
What else? So every time we talk about the CPU, central processing unit, I'm hearing this as a brain of the computer. So one of the things that human brain does that we are trying to get into computers to do is the actual thinking. So human can think, computers cannot think. Eventually they will do it. But if you go back to what is thinking and you want to analyze what the thinking is, if you ask me a question and I have the answer for you, the answer is actually stored in my brain somewhere. And when I'm talking to you, I go and reach that section of my brain, I get those information and bring it back to you. So when I'm talking to you, I'm constantly going and getting those information, and then I process it through how to tell you that information that I have. So the bottom line for the CPU is that it will fetch and execute instructions. So CPU is going to have some instruction that's just going to execute. So it's just going to look at the instruction, it's going to execute those instructions. If you are computer science, you will take an assembly language that's going to be talking a lot more detail on these things. So when it needs its instruction, the instruction is actually in a hard drive. So we call them secondary memory. Hard drive is in a solid state. It is not the memory, although it's getting closer and closer to be there. So not everything is going to fit in memory. Memories are expensive. We don't want to pay $5,000 for a computer. So we get a hard drive, which was CD, DVD, now is turning into more of a USB technology type of thing. And then it's going to bring it to the memory. So my CPU, the only thing that its CPU sees in the whole computer is this memory. It doesn't see anything else. The CPU doesn't know about my hard drive. It doesn't know about my USB drive. It doesn't know about the network. It doesn't know anything. That's why we call this main memory. So whatever instruction that the CPU wants to execute has to come from the main memory. So the operating system job is to go to the hard drive or anywhere else, bring the program. Because the program doesn't fit in the memory is expensive, so we don't have a lot of it. It's going to bring a piece of my program and put it in the memory. And from that memory, it's going to bring one instruction and put it right here. And then CPU is going to execute. And we're going to look at some of them, just a sample, and that's what's happening. And you're going to spend a lot of time in this in assembly language. So we're going to cover some in a high level, and then we can get into more detail. So when I write a program, I'm going to save, I'm going to compile my program. I'm going to, in C++, we're going to make it as a binary. CPU only understand binary. Binary means what?
0 and 1.
Zeros and 1. So the language of the computer is only 0 and 1. So somewhere, somehow, my program that I'm writing in English has to be changed to zeros and ones. A long time ago, a programmer had to write stuff in zeros and ones. I'm telling you, it's not that pretty. And then they went to assembly language, and they went to high-level programs that I am not worried about the binary thing. I'm just writing my program more like an English type, and then the compiler is the one that's going to be changing it to the binary. Since CPU is the main processing part of the computer, they don't want it to be busy all the time. So they came and create a mini CPU that's called ALU, Arithmetic Logic Unit. So the job of this ALU is just do the computation. So any computation that, so if I have an instruction over here that needs computation, then it's going to be sent to ALU. And the interesting things about computers is not that they are not doing the things that they are not doing things the way we are thinking. So we are thinking about multiplication. ALU doesn't know anything about multiplication. It knows about shifting and adding. That's all it does, shifting and adding. So when it gets, so we have a byte, which is 8 bits. So 1 bit is 0 or 1. And if I put 8 of them together, I'm going to have a byte. We organize it in 8 bits at a time, 1 byte. Right now, when you say my machine is 64-bit machine, that means it has 64 divided by 8 is 8 byte. Every instruction is 8 byte, 64-bit. One instruction is 64-bit. So ALU is just going to get that number or whatever it has, and all it does is shift it and add it. It does that for subtraction. It does that for division. It does that for multiplication. So that's what the job of ALU is. So CPU is not going to deal with it. It says, okay, you want calculation, go send it to ALU and it's going to do it for you. Main memory, the older computers, and we transitioning right now, is when we turn off the computer, the main memory would go away. So it's not, that's why we need hard drive and other devices to keep our stuff, because the main memory is going to go away. Remember, CPU only sees main memory. So when I turn my computer back on, the main memory does not exist. So it has to fill it up. And that's the job of operating system. Again, if you are a CS student, you will take a class in operating system, you will take a class in assembly language, and you will get more into these details of these things. So when I have my computer, I'm going to have my input devices and my output devices. The standard input would be a keyboard, the standard output would be the monitor. And the computer programs that we are going to be compiling for this class all the way to the end, and if we have time, we can do the GUI, is console programs, meaning that we're going to be displaying the output to the screen. We are not going to make a graphical user interface from it. Any questions about this quick note on this one?
Yes, I have a question, Professor.
Sure.
So I looked up my computer spec, the other class, then it says my computer has 8 CPUs, then the 4 is a performance, and the other 4 is a efficiency. Then can you explain like what does it mean?
Say that again, it's 8 and it's,
8,
okay.
Yeah, 8 cores, then the 4 is performance, and the 4 is the 4 are the efficiency. Then can you explain like how's difference performance and efficiency in the CPU process?
Okay, so CPU can only do one thing. So CPU can execute only one instruction. So that's all it can do. It cannot do any more than that. Now, they figure out that, okay, to make the program faster, maybe we need more CPUs. So for the mainframe and the bigger computers, they had more CPUs. So you have, instead of doing one instruction at a time, you would have multiple instructions going with multiple CPUs. But then with that, it would come complexity of it, that which instruction goes to which CPU, and when it's done, how do we put them together? Again, the detail of that is going to be part of your operating system. Then the technology advanced, and I said, okay, even though we have one CPU, we're going to make this CPU, build it, engineer it in a way that's going to look like much bigger CPU. So one CPU is going to be acting like 8 CPU. So it has some division, it has some areas on that one. So, and because it's one CPU, the complexity of it is going to be a little less. Of course, the operating system and all those things, if you get to that, and I'm not going to get to the detail of it. So now that we have a CPU divided into sections, then we can assign some different things to go to the different areas of the CPU. So that's where it says 4 of them is for this, 4 of them is for the other one, and that's the way it's assigned through the operating system. So that's what the core is about. When they say it has 8 core, it's just one that is acting like it's 8. And then 4 of them is going to be responsible for doing this task. 4 of them are responsible to do this task. So if I have something coming into my CPU and it's going to be about this area, it's going to go to that side. And it's about this area, you're going to go to that side. So it's going to be 4 in your orientation. If you were on a campus, you would go to the campus and say, I want the orientation. And they said, okay, if you're computer science, go to talk to that guy. If you are business, go talk to that lady over there. So that's what basically separating the tasks.
I see. Thank you much.
Okay. All right. So we're moving on. So talked about a little bit of a memory, binary, the bit and byte, and the address is a location of the instruction that I say inside the memory. So generally what we would have so things are going to be stored in a memory, and then every byte is going to be an address. So I can go to a specific byte and pick up something. So when I have my memory, the memory, remember I said that my whole program is not going to fit in the memory. So every program is going to have minimum requirement of how much of a memory does it need. And generally the program is going to be divided in 3 sections. So my code, my instruction is going to come into the first section. That's where my instruction is going to be saved. Not all of them, just a block of a bunch of block of my instructions going to be there. That's where it's going to be my code. Then I'm going to have a location for my data. And there's going to be a location when I'm running my program. So it's going to be a temporary location when I'm running my program. I'm not going to go through the detail of it right now, but that's the way things are going to happen. So if I want to go execute, if I want to go and execute, so my instructions is over here. So I'm going to pick up my first instruction from here. So it has to know where in the memory this first instruction is. So it's going to have the address of it, that what is the number of the byte that is right there. And of course, the next instruction is going to be next to it. So in our case, if I have 64-bit machine, if this address is 1 million, this one is going to be 1,000,064, and so on and so forth. It's going to add 64 in. In the data section, each one is going to be the size of the data that they have. So if it's going to have a variable, we're going to talk about the variables. It's going to be right here. The next one and the next one and the next one is going to be there. So that to get to them, I need the address. Lucky for us, because it's high level programming, I'm not going to remember the address, and this address is going to change all the time anyway, because this time is on 1 million, next time is going to be on 2 million. I don't have to worry about the addresses. I'm just going to create variables that's going to be turned into the addresses in when I'm compiling my program. Is going to be turning into the address. So I'm going to have a variable called salary that's going to have this address over here. But I don't have to remember where in the memory is. I'm just going to say salary. And when I say salary, it's going to go in here and it's going to translate it to this address over here. So the way that the addresses are is now it's starting with the 0, and then it's going to just add 1 for every byte that it goes on. The reason that we're doing the 0, there is some reasoning behind it, but let's not get it complicated right now. And in real life, the addressing is upside down, but we are not going to deal with that right now. It's going to get a little confusing. So if this address is 0, the next one is 1, 2, 3, 4, and all the way down here, 1 million, 1,000,064, and so on and so forth. So that's the way the addresses are. It's just like you come to my street and I say my house is house number 5 in this street. So first you're going to come to my street, and then you're going to go to house number 5. So that's what happens with the base memory address. You come to that address, and then you go to byte number 4, and you're going to get this one. So that's what the address is about. So we have our data, and the data can be big or small. Some of them are going to be big, and the C++ being efficient language is just going to try ahead of time to say, okay, if you don't need as much memory, then we are not going to give you that much memory. And that's why C++ has been around so long, because it's been very efficient language. And so before we run the program, the compiler is going to go figure out how much room do we need for the storage, and it's going to assign that. So when I'm running my program, I don't have to worry about the storage, it's already there. So if I look at the data section of my program, remember it's going to have the code on the top. I am looking at the memory. So when I get a piece of memory for my program, first part is for the coding, second part is for my data. So some data is going to take 3 bytes, some data is going to take 2 bytes, some data is going to take 1 byte, and some, so I'm going to be declaring them right after each other. And when I compile it, it's going to go and reserve a space in the memory for those things for me. So if my address of my data section is 1 million, of course, it's never going to be 1 million because it's always going to have some numbers at the end of it. But if it's 1 million, the first one is going to be 1 million. The next one is 1,000,001, 1,000,002, 1,000,003, 1,000,004, and so on. So if I have 3 bytes for the first one, then this one is going to start at the fourth. So 1 million, 1,000,001, 1,000,002, 1,000,003. So it's just 1 minus 4 minus 1. That's going to give me the address of this. So I will have a base plus this. Questions on this? So they find out that this binary thing is not working very well for everybody. I mean, at that time, people were thinking binary. Programmers were thinking binaries. So they figured out, okay, maybe we should do it a little different. Maybe we should have some way to change the binary to English and English to binary or some other things. They came up with this table. It's called ASCII table. And this ASCII table is an appendix at the end of your book. So that is going to have like a map that what keys are going to be mapped to what. So how many bytes is this? How many bytes is this? Wake up.
Right.
How many bytes is this one?
Wouldn't it just
Wake
be
up,
one
wake
byte?
up, wake up. How many bytes?
Wouldn't it just be 1 byte because it's 8 digits, like a binary? No, 8
Good.
bits. Yeah.
Very good. 1 byte
Right.
is 8 bits. So this is only 1 byte because it's only 8 bit. ASCII table is using 7 bit. And the last one is reserved for checksum. So it's going to be using 7 bit generally. Let me see where we're going to talk about this. So go away. Okay, my phone. Okay, 8:39. Okay, we have time. I'm trying to think how much we should talk today about these things. So if I look at the decimal number, which was created in Middle East, some people call it Arabic system. So the numbers in the system that we are using is based on 10. That means that I have numbers from 0 to 9. And if I want to go to, so I have numbers from 0 to 9 as a 1 digit. And when I get to 9 and I want to go to the next digit, I'm going to shift over and I put a 0 in there. So that is 10 in base 10 numbering. So if I have 385, what I do is I say it is 3 times 10 to the power of 2 plus 8 times 10 to the power of 1 plus 5 times 10 to the power of 0. So as I go from right to left, my digits are going to be multiplied by 10. So 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. That's the way we're going to use the binary system. I mean, the regular numbering system, base 10. Now, binary is base 2. When we say base 2, that means I cannot have 2 as a digit. I can have only 0, and I can only have 1. So if I go to 1, I want to go to the next one. It's going to be 1, 0. I shift to the left, I put a 0 on it. Because this is base 2, 1, 0 is going to give me 2. Remember, in base 10, 1, 0 would have given me 10. Base 2, 1, 0 is going to give me 2. Have you guys seen that the t-shirts some people wear? There are 1, 0 types of people, the ones who understand binaries and the ones who don't. So 1, 0 in binary means 2. And what they are saying is there is only 2 types of people. They understand binary and they don't understand binary. So the fact that 1, 0 is 2 in binary and some people don't know it, I guess that's what they're talking about. So if I am going to make this to a decimal number, I'm going to start with the first one, which is 2 to the 0, which is always 1. And I multiply to 2 as I go to the left. So that's going to be 1, 2, 4, 8, 16, 32, 64, and 128. So I'm just multiplying, and instead of thinking about what 2 to the 8, 2 to the 6, I'm just multiplying by 2. So 1, 2, 4, 8, 16, 32, 64. So this is 64 plus 1. That would give me 65 as a decimal number. So if I go to ASCII table, I can look at the binary one, or I can look at the number 65, and that's going to give me the uppercase A. So it is 65. Now, the one next to it, so if I have So if I have 0, 1, 1, 0, 0, 0, how many is that? 1, 3, 3, 6. Okay, this one. What does this give me? 0, 1, 1, 0, 0, 0, 0, 1. What is that in decimal number?
87.
No. This is 1, 2, 4, 8, 16. This is 32. This is 64. So it's going to be 64 plus 32 plus 1, which is
96.
97. So they call this bit as a shift. So if it's on, means it's lowercase. When it's off, it's uppercase. So the difference between the uppercase and lowercase is 32. So 65 is uppercase A, 97 is lowercase a. If you look at the ASCII table, that's the way is it in the decimal. Okay, so I'm just going to leave it like that for now. I am now, let me see what we got in here before I say something. So we talked about the main memory. That's the only thing that the CPU sees. That's what is called main memory. Whatever I need to run at the runtime has to be in the main memory. Otherwise, it's not going to work. So if I get the virus, my instructions in the main memory is not correct. That's why I cannot run a program, or in the case of operating system, I cannot run my program. So it has to be in the main memory to be run. Secondary memory is anything but main memory. So it can be your hard drive, it can be USB drive, a DVD drive, whatever we have in there. So hard disk are not as fast as memory, but it's much cheaper. So we need to use those. I don't know if anybody remember floppy disk, compact disk. I'll let you guys to read those stuff. Random access means I can go to a specific, remember this spot for your test. Random access, I can go to a specific location and find it. A sequential, I have to go through it. So if I say our classroom is in R207, you cannot just jump into the R207. You have to go to the second floor, you have to start with certain number, and you have to keep going till you get to the R207. You cannot just jump in there. But if you are on the first floor, you don't have to go sequentially. You can just go to the classroom right there. So random access, you can just access it directly. Sequential, you have to go through it. So in my time, we had tapes. So if I wanted to find a song to play, I had to rewind the tape at the beginning and look for the song that I want to play. I could not jump directly to the song I want to play. So that's the time we had. That's a sequential. I still use using those for storage because you don't look for things for the backup. For the backup storage, they still use tapes because it's very, very cheap, and they don't need to look for things constantly. They only need it when something goes wrong. So they would use it for the backup. So we talked about this operating system. So we have our program. We're going to be writing the program. This program is going to need some data. So the program is going to process this data through the computer, and it's going to give us some output. High-level languages, more closer to the English language, so we don't have to worry about the binaries and those kind of things. C++, C have been around for a long, long time. Java came after this to get some things differently. I was trained on Pascal, was a good language, but didn't last long. So some of these languages out there, high level. This is assembly language. You will learn that if you are a computer science or computer engineering or electrical engineering, you're going to learn assembly language. So the add X, Y, Z has to take the X to a location next to the CPU. It's called register, and it's going to. So the instructions can be different depending on the system that's using it. So in this case, it's going to add X to Y, and it's going to store it in Z. So an instruction is going to look like this. So this is called instruction. This is only 16-bit. They don't want to put a huge one, it's going to get us confused. So the first part is going to tell what needs to be done. So when the CPU sees this instruction, it's going to look at the 0110. It says, okay, 0110 means I have to add something. And when I want to add something, I have to know what is it that I'm adding to what. And that's where you're going to spend some time to learn more about these things. So these are the addresses of my registers, which are a small memory next to the CPU for storage. So that's where we're going to do these kind of things. It's funny that when I first started in PCC, we were spending 2-3 weeks on these things. I don't think we need that right now. So we write the program in a high-level language, and then we're going to use the compiler. The compiler job is 2 things. Again, be sure you know this for your test. Compiler job is 2 things. One is going to check the syntax. Syntax is like a grammar. So I'm going to have a checker that's going to check my grammar first. So I'm writing something, it's going to go in there and it's going to check the grammar. The grammar means what? That my code is in line with C++. So we're going to learn that, and we're going to figure out as we go along that it's going to check that. If the grammar is correct, then it's going to compile it to machine language, which is zeros and ones. And when we're running that the machine language, it's going to need some data that can come in from the user or from a file or from a database somewhere that's going to take that data and it's going to give us some output. So my program is going to add 2 number and it's going to display the result. So the 2 number, it may come in from the user. So when I'm running the program, it's going to ask for 2 numbers, and somebody's going to type in 2 numbers, and then I'm going to add it. I'm going to display the result. So sometimes, a lot of times, we don't have to recreate things that's going to be there. We might have some code that is already compiled. I don't have to compile it again. So we can reuse those things through the linker to add it to our program. So we can have potentially some code that's already compiled. It's not part of my program, but I can add it to my program through the linker before complete machine language. I'm not going to go through the history. You can read that on your own. How much time do we have? Okay. So, algorithm is a sequence of precise instruction that leads to a solution. You can think about it that when you go solve a calculus problem, you have to go through certain steps to get that derivative or multi-derivative or something that you're trying to do. So it's the instructions of how do you get the solution. And of course, our program is going to be that steps, those steps in a specific language. So we need to do this one, and this one to get this result. So if I want to, how many times a name occurs in the list, I have to set up certain steps. So first one is getting the list. Second one is what is it that I'm checking. Then I'm going to set the counter to 0. And then we're going to be looking at the first one, second one, third one, and as soon as I find it, I'm going to get the answer back. So these are the steps that we're going to be using to get our algorithm done. So when we are designing a program, and I am fond of design, so we're going to be pressing on that one a lot. The question is going to come up. It says, okay, what is it that coming into it? What is going out of it? And how is it organized? So we can think about it as a manufacturing. So if I have a manufacturing for a manufacturing, I'm going to have some raw data that's coming into my manufacturing, and then I have my product that's going out of this. And then I'm going to do this processing. So in general, we might call it IPO, that is input, processing, output. So the data is going to come to me, I'm going to process it, and I'm going to have an output going out. So the processing part is what we're going to be doing in part of our program. Questions so far? Okay, I do have another class right after this class. So if you have some questions, you're going to talk to me right